Use the properties of logarithms and the logarithmic property of equality to solve the logarithmic equation. We have 2 log of x plus 4 equals log of 32 plus log of 2. So there are several properties of logarithms that we're going to use, and we'll also use this logarithmic property of equality. So let me tell you about that, because this property here will help us to understand what we're working towards. So the logarithm property of equality is when we have log base b of m equals log base b of n, and this tells us that m equals n. The background of this property is that logarithms are 1-to-1, and so if we have y values that are equal, those x values must be equal. But the reason why I wanted to show you this is because it's revealing to what we're working towards. We're working towards having a single log on the left and a single log on the right, and you'll notice no coefficients on those logarithms. So when I look at the example that we have, I notice I do have a coefficient, so I want to remove that coefficient. And on the right hand side, you'll notice that instead of just 1 log, I have 2 logs. So working towards having a condensed log on the left and a condensed log on the right reveals what I need to do. I need to take care of that too. I'm going to take care of that too with what we call the power rule for logarithms. And the power rule for logarithms is when you have log base b of m to a power. That's the same as the power times the log base b of m. So that means that we're going to be able to take this coefficient and move it into the power. So on the left hand side we'll have log of x plus 4 squared. So we move that coefficient to become the power on what's inside the log. On the right hand side, that plus sign indicates that we're going to use the product rule for logarithms. And the product rule for logarithms is when we have log base b of m times n. That's equal to log base b of m plus log base b of n. So having these logs with the same base added together means that we can condense them to a product. So condensing them to a product would be log of 32 times 2, which is log of 64. So we have log of x plus 4 squared equals log of 64. So now we've got it to the state where we can use the logarithm property of equality. We have logs with the same base on both sides. What's inside those logs must be equal to each other. So x plus 4 squared is equal to 64. And we can solve for x by taking the square root of both sides. The square root and the square cancel each other out, leaving us with x plus 4 equals plus or minus the square root of 64, and that's 8. And I'll subtract 4 on both sides, and I have x equals negative 4 plus and minus 8. Negative 4 plus 8 is 4. Negative 4 minus 8 is negative 12. Now with every log equation, with every log equation, we need to check to make sure that we didn't get an extraneous solution. So let's check x equals 4 in the original. That's 2 log of 4 plus 4 equals log of 32 plus log of 2. And the way we check is by making sure that we're never taking the log of a negative. So 4 plus 4 is a positive. We'll keep that solution. Let's check the other one. Let's check x equals negative 12. That would give 2 log base 10 of negative 12 plus 4 equals log of 32 plus log of 2. And you can see here, negative 12 plus 4 will be negative 8, and the log of a negative is undefined. So we're going to have to throw that solution away. So the only solution to this logarithmic equation is 4. X equals 4 is the solution. 5. The population of Adamsville grew from 10,000 to 15,000 in 7 years. Assuming uninhibited exponential growth, what is the expected population in an additional 3 years? So we have this sentence that says, assuming uninhibited exponential growth. That will tell us the formula that we're using. So we'll use the formula P of t equals P naught e to the kt. So P naught, that is our initial population. K is our growth rate. T is time. And P is our population after time, after a certain time period, T. So this information in the first sentence, the population of Adamsville grew from 10,000 to 15,000 in 7 years. So we've got a starting population of 10,000. It grew to 15,000 in a time period of 7 years. You can see that we're given 3 of our 4 variables, so that means that we're going to be able to solve for the growth rate of K for this city, the growth rate of this city. And once we know the growth rate of this city, we'll be able to figure out what the population will be with an additional 3 years. So we're going to substitute into our formula these values. We grew to a population of 15,000 starting from 10,000. And we have e to the k times 7. I'm going to start solving this exponential equation by dividing by 10,000. We get e to the 7k on the right. On the left, we can reduce. We can cancel those zeros out. We're canceling out factors of 10 when we cancel those zeros out. And then we can reduce 15 over 10 using a factor of 5. 5 goes into 15 3 times, 5 goes into 10 2 times. So we've got 3 over 2 equals e to the 7k. Now we're going to solve the exponential equation by doing the natural log on both sides. We have natural log of 3 over 2 equals natural log of e to the 7k. Natural log and e are inverse operations of each other. They cancel each other out. We get 7k on the right-hand side. So we have natural log of 3 over 2 equals 7k. And I'll be able to solve for k by dividing by 7 on both sides. We get natural log 3 over 2 over 7. So we have our growth rate for our population. And now if we want to find out what the population will be with an additional 3 years, we can do that. And there are 2 different ways you can approach it. We want to find an additional 3 years. So if you want to use a time of 3 years, you're going to start from the 15,000 to use 3 years. But if you want to use the original 7 years plus 3 years, you're going to use 10,000 as your starting population. So let's write it out in both ways. So if you're only doing the additional 3 years, then your starting population will be the 15,000, and you'll use the k that we just found, natural log of 3 over 2 over 7. But if you're going to use the total years, you're going to use a starting population of 10,000. And of course that k that we just found, the natural log of 3/2 over 7. So if we use the 3 years, it would be p of 3 equals 15,000 e to the k, which is natural log of 3/2 over 7, times t, which is 3. And if we use the 10 years, it would be p of 10 equals 10,000 e to the natural log of 3/2 over 7 times 10. We'll type both of these in the calculator, and we should get the same amount with both calculations. Now to make it a little easier to type in the calculator, I like to type the time in the front of the log. So we're going to type 15,000 e to the 3 natural log of 3/2 over 7 and 10,000 e to the 10 natural log of 3/2 over 7. So let's see that in the calculator. I'd really like for you to try it in your own calculator to make sure that you know how to type this. Yeah, I think I might have closed my calculator. Let me get it open back up. So a lot of my students have issues typing in the calculator. Most of the issues have to do with parentheses, but there can be other issues with certain versions of calculators if you don't know how to type things in there. So give it a try with your calculator. We've got 15,000 e and we want to type 3 natural log of 3/2 divided by 7. And we get that the population grows to 17,846. And if we're rounding, we can round to 47, 1,700, 17,847. So let's try the other one. We should get the same answer. We've got 10,000. E to the 3 natural log of 3/2 over 7. And I apologize, I typed a 3 here instead of the 10, so let's try that again. I want to change this 3 to a 10. And there you can see we get the same answer, 17,847. Use the graph of y equals 3 to the x and transformations to sketch the exponential function f of x equals negative 3 to the x plus 4. Determine the domain and range. Also determine the y-intercept and find the equation of the horizontal asymptote. So in this question, I want to start off by getting the points that are on the original graph. So we have our base graph of y equals 3 to the x, and let's choose the points -1, 0, and 1, and we'll substitute that into our equation. So that's 3 to the -1, 3 to the 0, and 3 to the 1. 3 to the first power is 3, 3 to the 0 power is 1, and having a negative in the exponent would do the reciprocal of the base, so we get 1/3. Now we want to see, using transformations, how those points transition in the graph of -3 to the x plus 4. So first we have to understand what these transformations are. So in f of x equals -3 to the x plus 4, we've got two transformations. We've got that negative and we've got that plus 4. So having that negative that's multiplied onto our function is a transformation of a reflection. Now there are two types of reflections. You can reflect vertically over the x-axis, or you can reflect horizontally over the y-axis. Now this position of this negative tells us it's a vertical reflection. So because it's located outside of our base function, it's a vertical reflection. If that negative was located here inside the base function, it would be a horizontal reflection. So we're going to reflect vertically. Now the plus 4 is going to be a shift. Adding and subtracting is always a shift. Now when we add inside the base function, it's going to be a horizontal shift. The horizontal shift will shift either left or right. and because it's a plus, it's going to shift to the left. Now, if that plus 4, so that plus 4 is in the exponent inside the base function, if that plus 4 was out here, that would be a vertical shift instead, and that would shift up. The plus would be up. So because it was inside the exponent, it's a horizontal shift to the left. So we want to think about these ordered pairs. Let's start with the ordered pair 1, 3. So if we have the ordered pair 1, 3, and we do a shift to the left, a shift to the left is going to affect the x-coordinate. So moving to the left will subtract 4 from that x-coordinate. So if we subtract 4 from that x-coordinate, it's going to move to negative 3, 3. So that's that shift left, subtracting 4 from the x-coordinate. But then I also want to do a vertical reflection. A vertical reflection will take anything that is above the x-axis and mirror it below, and anything below and mirror it above. So when we think about that, as far as the ordered pair goes, these two ordered pairs would have the same x-coordinate, so it's not changing the x-coordinate, but the y-coordinates are going to be opposite of each other. So with a reflection, so to reflect vertically, that's going to change the point to be negative 3, negative 3. So the x-coordinate stays the same, but the y-coordinate becomes the opposite. And we're going to do the same thing with the rest of these ordered pairs. So if we start with an ordered pair of 0, 1, if we shift it to the left 4, we're going to subtract 4 from the x-coordinate, and that's going to move it to negative 4, 1. And then if I want to do a vertical reflection, I'm going to mirror that y-coordinate. So it becomes negative 1. Then the last point is negative 1 and 1/3. I'm going to subtract 4 on the x to shift it to the left 4. That becomes negative 5 and 1/3. And then when I do the vertical reflection, it's going to mirror it and become negative 5 and negative 1/3. So those 3 points have moved to their new positions. And we also want to sketch the graph, find the domain and range, the y-intercept, and the horizontal asymptote. Okay, so let's do those pieces. So if you'll remember your original graph, y equals 3 to the x, is a graph that looks like this. And it has a horizontal asymptote at y equals 0. Now we are sketching the graph. We've found these new points. These are the new points on our graph. Negative 3 to the x plus 4. So that's negative 3, negative 3, negative 4, negative 1, and negative 5 and 1/3. So our new graph looks like this. And remember, it's reflected vertically, so that's why we were going to infinity and now we're going to negative infinity because of that reflection. But you'll see that we still have the same horizontal asymptote that we had before. So the horizontal asymptote is still y equals 0. Okay. We also want to find the domain. The domain is going to be all real numbers. The range is going to be negative infinity to 0, because you can see it's below the x-axis. And then we have, we want to find the y-intercept. So we find the y-intercept by letting x equal 0. So let's substitute a 0 in. We would get negative 3 to the 0 plus 4. That's negative 3 to the 4th. And that's negative 81. So we have a y-intercept of 0, negative 81. And I think that's all the parts. We found the domain, the range, the y-intercept, and the horizontal asymptote is y equals 0. On this example, we want to use the graph of y equals 3 to the x and transformations to sketch the exponential function f of x equals negative 3 to the x plus 3 minus 3. Determine the domain and range, determine the y-intercept, and the equation of the horizontal asymptote. So let's start with our base graph of y equals 3 to the x. Y equals 3 to the x, we can get those ordered pairs. Negative 1, 0, and 1 is what we choose for our x's. For our y's, we'll get 3 to the negative 1, which is 1/3. 3 to the 0, which is 1. 3 to the 1, which is 3. So that gives us a sketch of our original graph. 0, 1, 1, 3, and negative 1 and 1/3. That original graph has a horizontal asymptote, which is right on top of our x-axis y equals 0. So we want to use this starting point to graph this function, f of x equals negative 3 to the x plus 3 minus 3. So we've got several transformations here. We've got this negative. Okay, this negative is going to be a vertical reflection, and that's going to reflect over the x-axis. Then we have this plus 3 here. The plus 3 is going to be a horizontal shift. And that horizontal shift, because of the plus, is going to shift left 3. Sorry, my pen is not cooperating. We're going to shift left 3 because it's a plus. And then we have this transformation here, this minus 3. This is going to be a vertical shift, and it's going to shift down 3. So we're going to use these transformations to see how this point is moved. These 3 points here get moved to our new graph. So we have the ordered pair. Let's start with nice numbers, 1, 3. So with these ordered pairs, we want to shift to the left 3, So to shift it to the left 3, that's going to subtract 3 from our x-coordinate, and that's going to move it to negative 2, 3. And then we're going to do our reflection. And our reflection is going to make our y become the opposite. So for our reflection, we multiply a negative 1 onto our y-coordinate. So that's going to become negative 2, negative 3. And then finally, we're going to shift down 3. That's going to affect our y-coordinate by subtracting 3. So that becomes negative 2, negative 6. So those 3 transformations moved our point from 1, 3 to 2, negative 6. Okay, so we'll go with our other one with nice numbers. The last one has fractions, so we're going to have to get a common denominator to do some of that math. So with our horizontal shift, we're going to shift left 3, so that's subtracting 3 from the x. That gives negative 3, 1. Then we're going to do our reflection, multiply negative 1 times the y. That's negative 3 times negative 1. And then finally, we're going to shift down 3. So we subtract 3 from our y. And that moves us to the point negative 3, negative 4. Okay, last point is negative 1 and 1/3. And we're going to shift to the left 3, so subtract 3 from our x. That makes our x-coordinate negative 4. Then we're going to do our reflection, multiply by negative 1 on the y. We get negative 4, negative 1/3. And then we're going to shift down 3, so we're subtracting 3 from our y. And here's where we have to get a common denominator. We need to do negative 1/3 minus 3. We'll treat that as 3 over 1. And I need a common denominator, so I'll multiply by 3 over 3. That's negative 1/3 minus 9/3, and that is 10/3. So we get negative 4 and negative 10/3 for our final ordered pair. So to sketch our new graph, let's use these 3 new points that we got. And that will give us negative 2, negative 6, negative 3, negative 4, and negative 4 and 10/3. So 10/3 is about negative 3 and 1/3. Negative 3 and 1/3 be about right here. Now, we did shift down 3, so our horizontal asymptote will also be shifted down 3. So our new horizontal asymptote will be at y equals negative 3. And here's a sketch of our graph. And we need to state the domain. The domain of all of our exponential functions are all real numbers, negative infinity to infinity. The range will go from negative infinity to negative 3, where that horizontal asymptote is. And we need to calculate our y-intercept. So we're going to let x equal 0. F of 0 is negative 3 times 0 plus 3 minus 3. That's negative 3 to the 3rd minus 3. That's negative 27 minus 3, and that's negative 30. So we get our y-intercept at 0, negative 30. So the horizontal asymptote started off at y equals 0. And we're going to shift it down 3. So it started off at 0, and when you shift it down 3, it gets to negative 1/3, negative 3. Y equals negative 3. Shifting the other transformations, the transformation of reflecting it and the transformation of shifting it to the left, has no effect on that horizontal asymptote. If you take a horizontal line and you try to shift it left or right, it's going to be right on top of the old line, so that has no effect on it. And when you do a reflection would normally have an effect, but because your horizontal asymptote is y equals 0 and it's right on top of your x-axis, it doesn't have any effect. Your reflection takes things that are above and mirrors it below, or takes things that are below and mirrors it above. So the vertical reflection doesn't affect it. So the only effect is the vertical shift. If there is no vertical shift, then the asymptote is going to stay y equals 0. Solve the exponential equation. 4 to the 3x minus 3 equals 9 to the x plus 1. We're going to solve this by taking the log of both sides. You can solve this by converting it to a log as well. But typically, on these problems, at the very end, we're going to type it in our calculator. And your calculator is going to have the natural log button on the home screen. If we convert it, we have to use a base 4 or base 9, and your calculator may not be able to type that in, or it might be in a hidden menu and it's a little bit harder to find. So I'm going to do this by taking the log of both sides. So we'll do natural log on the left and natural log on the right. And once we introduce the logs, we can use our log properties. The property that we're going to use is the power rule for logarithms. We're going to move this power into the coefficient. We'll have 3x minus 3 natural log x equals x plus 1 natural log 9. And then we'll use the distributive property to get rid of these parentheses. So using the distributive property, I'll distribute natural log of 4 to 3x and negative 3, and I'll distribute natural log of 9 to x and 1. This will give 3x natural log of 4 minus 3 natural log of 4 equals x natural log of 9 plus natural log of 9. Now I'm going to collect the x's to one side and all the terms without x on the other side. I'm going to subtract x natural log of 9 so that I can collect both x's on the left-hand side. And I'm going to add 3 natural log of 4 so that I can have the terms without x on the right-hand side. So that's going to give 3x natural log of 4 minus x natural log of 9 equals natural log of 9 plus 3 natural log of 4. Now that the x's are collected on the left, I'm going to factor out the x to leave 3 natural log of 4 minus natural log of 9. The right-hand side is the same, and now I can solve for x by dividing by 3 natural log of 4 minus natural log of 9. That gives x equals natural log of 9 plus 3 natural log of 4 over 3 natural log of 4 minus natural log of 9. So, since we mentioned the calculator at the beginning, let's get our calculator out and see how it looks. Now, a lot of people have trouble typing this in the calculator. Most of the time, it has to do with parentheses. Every once in a while, it's something else. So, actually, before I start typing it in the calculator, let's talk about the parentheses that we're going to put in and what your calculator needs to know. Now, when we write this out like this, we know that the 9 belongs to the natural log. The 9 is substituted into the natural log function, but your calculator needs you to be more specific. So when you type natural log in your calculator, it's going to automatically put a parenthesis here, and you have to close it out when you're done. So your calculator will put a parenthesis here, and you need to put a parenthesis here so that your calculator knows that the 9 is in that natural log. It's going to do that for all of the natural logs, so it'll do it here as well and here. So you're going to have all of those parentheses so that your calculator knows what goes inside each one of those logs. Okay, in addition to that, the way that we have this answer written is in fraction form. That fraction bar means division. And we're going to type the division button in our calculator for this fraction bar part. But your calculator needs to know what goes in the numerator and what goes in the denominator. So we're going to have to add in some parentheses here so that your calculator knows what is the numerator and what is the denominator. So you're also going to put parentheses here and here to indicate what's in the numerator, and here for the denominator. So let's see what that looks like. So I'm going to start off with the first parenthesis, natural log of 9 plus 3 natural log of 4. And I'm closing parentheses here. So notice I closed the parenthesis after that 9, and I'm closing the parenthesis after that 4. And I'm going to do one more parenthesis because that closes out the whole numerator. And I've got division. Open parenthesis for the denominator, and we have 3 natural log of 4. I'm going to close that parenthesis, minus natural log of 9. Close parenthesis for the log, and close parenthesis for the whole denominator. So we've got 3.240, and let's round to that fourth decimal place, so we'll make that a 2. 3.2402. Make sure you're trying this in your own calculator to see if you get the same answer, and practicing to make sure you get those parentheses right. Use properties of logarithms to rewrite the expression as a single logarithm. Whenever possible, evaluate the logarithmic expressions. For this example, we have natural log square root x minus 1/3 natural log x plus natural log 4th root of x. So our goal in this problem is to write it as a single logarithm. What we notice here is that all of the logs have the same base. These are all natural log, which are all base e. So they need to have the same base for you to be able to use the properties that we're going to use. So we're going to use the product rule and the quotient rule. And with the product rule and the quotient rule, these are going to allow us to condense these logs down to a single log. So let's take a look. We're going to have, for the product rule, we have log base b of m plus log base b of n. So notice the plus here. This is where we're going to use the product rule. And inside the log, we write log base b of the product, m times n. And with the quotient rule, we're going to have subtraction instead. Log base b of m minus log base b of n. So you'll notice here we have subtraction. We're going to use the quotient rule there. And inside the log, we get log base b of the quotient, m over n. Okay. Now, before we can use those two rules, we have to use the power rule for logarithms. So you'll notice that we have a coefficient in front of this log. So we're not able to use our product rule or our quotient rule until we've gotten rid of all of the coefficients. So the way we get rid of the coefficients is with our power rule. Our power rule will have something like this: p log base b of m. So if we have a coefficient, we're going to write that as log base b of m to the p. The coefficient becomes the power, which is why this is called the power rule. So let's start with that. We'll move the power, move that coefficient to the power, and we have minus natural log of x to the 1/3. I want to make these the first and the last terms look a little bit more like the middle term. You'll notice we have that fractional power. So one of the things you want to remember is that when you have radicals, that's the same thing as the fractional power. So we can write the square root of x as x to the 1/2 power. And we can write the 4th root of x as x to the 1/4 power. So now all of them are using the same format with the powers instead of the radicals. So now that we've gotten rid of that coefficient, we're now able to use the product and the quotient rule to condense. So when we condense, we're going to condense down to a single log. And when we condense, we're going to use multiplication and division. So when we have addition, we're going to use multiplication. When we have subtraction, we use division. So we do have a subtraction, so we're going to have some division. We're going to have an x3rd in the denominator. And we have addition, so we'll use multiplication, x to the 1/2 times x to the 1/4. So on this step here, I used both the product and the quotient rule at the same time. This log is positive, and this log is positive. So that's why the x to the 1/2 and the x to the 1/4 went in the numerator. This log is negative. That's using the quotient rule. So the x to the 1/3 went in the denominator. Now, usually with a problem like this, we would be done at this step once we have used the product and the quotient rule. But this example is special. It's special because all of our factors have the same base of x. Because they have the same base of x, we can use some exponential properties to combine all of this together. So we have, this might be confusing because we use the same names. We have the product rule for exponents, and with the product rule, we add those exponents together. We also have the quotient rule for exponents. That's when we're dividing, and we subtract the exponents. So those rules look like this. B to the m times b to the n. When we're multiplying with the same base, we add those exponents together. When we're dividing with the same base, we subtract the exponents. So that's what we're going to do on the inside of this log. So we're going to do x to the 1/2 plus 1/4 over x to the 1/3. So I need to combine those together. 1/2 plus 1/4. I need a common denominator. So I'll multiply by 2 over 2. That's 2/4 plus 1/4 is 3/4. So that's natural log of x to the 3/4 over x to the 1/3. And that was using the product rule for exponents. And now I'll use the quotient rule for exponents. That's x to the 3/4 minus 1/3. Subtracting those exponents, and once again I need a common denominator. 3/4 minus 1/3. The common denominator is 12, so I'll multiply by 3 over 3, multiply by 4 over 4. That's 9/12 minus 4/12 is 5/12. So we get our final answer, natural log of x to the 5/12. Let me zoom out so you can see all that work. We used a lot of different properties and adding fractions together as well to condense to a single log and then condense using our exponent rules. Solve the system of equations using the elimination method. We have 6x minus 4y equals negative 12, and 7x minus 5y equals negative 16. Now we want to use the elimination method, and the problem is set up almost for us to use it right now. The first step is to make sure that you have all of your like terms lined up. Your x's, your y's, your equal sign, and your constants. And once you have your like terms lined up, you're going to decide which variable you're going to eliminate. You're going to eliminate x or y. So let's, it doesn't matter which one. I'm going to go with y just because the numbers are a little bit smaller. And what you need to do is look at the coefficients. We have a coefficient of 4 and 5, and you want to find the least common multiple of 4 and 5. And that's going to be 20. Some people think of it as common denominator when you deal with fractions, but the general term is least common multiple. So that's 20. We want to force these coefficients here to be 20 and negative 20. We want to have one be positive 20 and one be negative 20. So let's let the first one be the positive 20. So I would need to multiply by negative 5 to get the positive 20. And let's make the second one be the negative 20. I would need a 4 to multiply by to get the positive 20. So when we do this multiplication, we're going to multiply every term by those numbers. And our new system is negative 30x plus 20y equals a positive 60. And the second one is 28x minus 20y equals, and I don't know 16 times 4 in my head, so we've got 64. And that's going to be a negative 64. So now we've got exactly what we want. We're planning to eliminate the y's, and the y's have coefficients of the same number with the opposite sign. So now we're going to add these equations together. We add the like terms together. Negative 30x plus 28x will be a negative 2x. The y's will eliminate. 60 minus 64 is a negative 4. And now we have an equation with just one variable. We're going to divide both sides by negative 2, and we get x equals 2. And we can substitute this back into either equation to find the other variable. So we'll use 6x minus 4y equals negative 12, and let's substitute a 2 in for x, and that will give 6 times 2 minus 4y equals negative 12. That's 12 equals negative 4y equals negative 12. I'm going to subtract 12 on both sides, and I have negative 4y equals negative 24. Divide by negative 4, and I have y equals 6. So this gives us our solution 2, 6 to that system of linear equations. Use the properties of logarithms to rewrite the given expression as a single logarithm. Whenever possible, evaluate logarithmic expressions. On this one, we have log base 6 of x plus 5 minus log base 6 of x plus 4 minus log base 6 of square root 3x. So on this example, we're going to use the properties of the product rule and the quotient rule to condense this down to a single log. We are allowed to use those properties because these logs all have the same base. We don't need to use the power rule on this example because I noticed that none of these logs have any coefficients other than 1. So we can skip using the power rule, go straight to using the product and the quotient rule. So we're going to condense to a single log, and I've got some minus signs here, so I'm going to use the quotient rule, and the x plus 4 and the square root of 3x both go in the denominator because of this minuses. The x plus 5 goes in the numerator because that log is positive. So this would be our condensed expression, log base 6 of x plus 5 over x plus 4 times square root of 3x. We want to graph the inequality x squared plus y squared is less than or equal to 36. So this is an inequality in two variables, and we're going to graph that in two dimensions. So there are two parts to this type of question. We are going to start with the boundary. And the boundary will be x squared plus y squared equals 36. So what I've done is change that inequality symbol, less than or equal to an equal symbol. And when we graph this boundary, we want to graph this boundary with a solid line. The solid line indicates that the boundary is included. The reason I've chosen a solid line is because of this equal to here. Remember, our boundary is equal to, our inequality has equal to, so our boundary needs to be included in the solution, in the answer. Now this equation, x squared plus y squared equals 36, is in the format of a circle. It has a center of 0, 0 with a radius of 6. So we're going to graph, we're going to find 0, 0. We're going to move 6 to the right, 6 up, 6 to the left, 6 down. Those are all points on our circle, and we'll sketch the rest of our circle by connecting those 4 points together. And remember, I was graphing that with a solid line. Okay, so finishing up the shading on this, we are allowed to use 0, 0 as the test point. Since it is not on the line. We're going to substitute that into the inequality to get 0 squared plus 0 squared is less than or equal to 36. That gives 0 is less than or equal to 36, and that inequality is true. 0 is less than 36. So our test point was inside the circle, and our test point came out true. So that means that we're going to shade inside the circle. So in my math lab, you would choose the paint bucket and click any point inside the circle, and it'll fill in the shading for inside of that circle. So here we have the circle itself, and all of the points inside the circle are points that make this inequality true. Thank you for checking out my videos. Have a great day.